Hello, gentlemen and ladies in the auditorium. Welcome to our expert talk of today. It's my pleasure to have you here virtually around me assembled. We will start immediately when my backstage will put the first question up to the editor. I think my backstage want to put the question in. And here we start. The question goes to EPC, to Federico. How can GaN node drive inverters can be optimized with respect to GaN converters used in other applications like DC-DC converters?
Yeah, thank you for the introduction. I'm Federico. I'm application engineer at Efficient Power Conversion in the Motor Drive Application Center. So regarding the first question, gallium nitride devices are, of course, associated to high speed, high frequency operation, and that is mainly due to the fast transitions that are associated to the gallium nitride devices. In motor drives, these transitions are intentionally slowed down to not to exceed the maximum DVDT that can be applied to the rotor windings. So usually in DC to DC converters, a certain amount of decoupling capacitors are used to reduce the overshoot and ringing on the switching node. But these side effects are much less visible on motor drive inverters since the transitions are much slower. So basically in motor drive inverters you can remove, if you do a good layout, these decoupling capacitors. So reducing the bill of materials and also optimizing the total area of the converter.
Thank you, Federico.
I had a short question, Bodo, to Federico regarding the gallium nitride, if it's okay.
Mm-hmm.
Yes.
Yeah, looking at your article, I see your investigation are we're talking mainly about discrete components. So my question would be, do you investigating also in gallium nitride power module solution, especially for this 100 volt, 200 volt application, when I understood properly, or your focus is just discrete components?
Actually, yeah, I investigated both the discrete solution and the integrated circuit solution, because APC has both discrete FETs and monolithic integrated circuits. And on the motor drive application side, we do have reference design for both the discrete and the integrated circuits products that we have. So I have done this analysis is effective in both cases.
Okay.
Thank you.
Thank you, gentlemen. We are looking for the next question coming up.
Can I ask a question before we switch topic?
It's addressed to Infineon, to Guilherme, Bueno, Mariani. I hope I got it right.
Yeah, but
why use wide bandgap devices on motor drive applications?
Yes, okay. I can answer the question, but I think James had another question before for Federico, if I understood correctly.
Okay, then sorry.
Okay, so a quick question regarding for Federico. From EPC, you have your product has 100 volts, you have 650 volts. And is EPC planning to look into 1200 volts level devices?
Can I take this? This is Marco Palma. Actually, we don't have 650 volt. EPC is concentrated in the low voltage arena for GaNFET. So our biggest is a 350 volt, but it's still a small device. Our workforces are mainly in a 200 volt, 150 volt, 100 volt. And no, in this moment, we're not planning to go to the 650 and the 1200 volt.
I see in the market, because theoretically, GaN can have better, even competing like silicon carbide. GaN has more theoretical, higher blocking voltage feature. That's from the textbook, I understand. But in the market, I already see some 1200 volts level GaN devices. Do you think they are mature, or there are some still challenges? I know EPC is not looking into that, but maybe you have the answer for me.
No, I'm sorry, I don't have an answer for that, you know.
Never mind, I asked the wrong question then. Thank you.
We converge on the low voltage. But by the way, just one comment, that's the way to do is write the question on the chat, and then they would be.
Oh yeah, it's more pleasant. It's not yeah, okay. Yeah, it's in parallel then. Thank you. I'll take it offline. Thank you, sir. Yeah. Thank you. Yeah, okay, I'm good.
Okay. So let me present myself. So my name is Guilherme. I work for Infineon as a product application engineer. And I am responsible for motor drives, high voltage. So and regarding the question about wideband gaps on motor drives, so my vision is that we are looking for new ways to have higher efficiency. And I know that wideband gaps have some challenges to be employed on motor drives, but it also opens a lot of possibilities. And the vision that I try also to push forward also for motor design people is that now that we have this possibility of switching faster, we could rethink the way that we design motors. So I think that if we're looking for higher efficiency in the future, we should not just look at the inverter or the motor, but on the system level and try to push forward. And wideband gaps is a way of rethinking the way that we drive the motors.
Thank you, Guilherme. I want to make a little comment to the previous little discussion. There is the GaN, mainly the horizontal structure at the moment, and there is very little research for vertical. I think if there is more research for vertical, we may receive higher blocking voltages. That's just a feeling looking to the whole picture. But if we go vertical with GaN, SiC is already there as a vertical device element. So the question in some cases is, if we go to motor drive at higher voltages, SiC will be the first choice. It's just my impression. And now I just wanted to add that because it was a little bit unclear to me. Let's continue, Guilherme. You answered any questions from the other authors?
Sorry, I think I answered the question, but if you have any other question, I'd be glad to answer.
I'm fine. I'm fine. I just wanted
for sure.
to make my little comment to the
for sure.
previous crosstalk.
Maybe also one question to Guilherme from my side regarding the usage of wideband games for motor drives. I think also Guilherme mentioned his vision, and we know also the limitation for the motor drives to go for higher switching frequencies, which will be the benefit of wideband games. Do you see maybe in near future or in long-term future any solution coming up to support this high switching for motor drives without sacrificing motor lifetime, or do you see that mainly the primary target using wideband games motor drives will remain to improve efficiency with staying at switching frequencies below 50 kilohertz, let's say, as example?
Yeah, for sure. The thing is that, for example, when you talk about a motor, you can think about a general motor is going to be really high inductance for wideband gaps. We have these new motors that use, for example, PCB stators, and the inductance is really low there. And there you have no escape. You need to switch faster. And the idea of this kind of motor is that you can have lower volume. I know that's still not mainstream, but I think it's one way that we could design new motors, and we need to have wideband gap there because we need to switch faster. For really big motors, we already have these ceramic coating bearings. That is one of the problems, right, to using this faster switching, is because we have these problems in the bearings. There, the problem is still price, but I think that before we couldn't even switch that faster. And I think that with this new possibility, people should restart thinking, okay, there is no way that we could do this cheaper in order to be able to put both things together and have a better motor. So I think there is solutions for the problems. It's just that they were not investigated before, mainly because there was no possibility of switching that fast at the time.
May I add on this that if you look on the scenario of the low voltage, I'm talking about 48 volt, 96 volt, and 120 volt DC bus motors. This is already happening. So we're already talking about 100 or 120 kilohertz PWM frequency. And the reason is those motors usually are smaller, and their impedance on frequency is dropping at that frequency. So you get an advantage in the motor by simply increasing the PWM. By keeping everything else the same, with the gallium nitride inverter at a low voltage, you can increase the frequency, the PWM frequency, you can decrease the dead time, and then the same motor, as long as the motor is not flat in frequency, becomes more efficient. And that is already happening. We currently have customers which are even switching at 400 kilohertz, but these are a little bit more, let's say, on the right side of the Gaussian curve, while most of our customers are in the range of 100 kilohertz, where, by the way, there is also sweet spot for ceramic capacitor technology. And so this is also giving a help by changing the input DC bus capacitor from electrolytic to ceramics.
Thank you, Marco. It's a question to Vincotech. In figure 4, there are some inconsistencies in the marker description at TJ max 150 degrees Celsius. Is this a typo, or how can this be explained?
Oh, thanks for this question, because it's important. Yeah, it's a typo, unfortunately, and I was a little bit shocked when I saw this. This was a typo with our graphic designer, and it's a pity because these two graphs should convey the more important message that we attend with this article. So for the figure before on the upper graph, of course, the two markers should be silicon carbide and not silicon. Here we are showing what is the current power cycle capability with standard solder compared with silicon. So, and for the bottom part of the lower part of the figure 4, at T-junction maximum of 150 degree, the markers are switched. Of course, here the red triangle should be is the silicon standard, and the blue marker is silicon carbide with a new solder, showing that with a new solder we are achieving, compared with a standard solder, factor 9 higher power cycle capability. So yes, it's a typo, and I have to apologize for this, because as I said, this was the main message that I would like to convey, the improvement of this power cycle capability.
Thank you for making that clear. Typos always make big impact sometimes. Generations of kids were told to eat spinach because it's healthy and great. There is so much Fa, I would say steel in it. And finally, it came out that some funny guy had once said, if we have spinach, we can build a steel fab on it. So finally, they found out that somebody who did the analysis on spinach had 1,000 in factor misleaded to what it's real in, and any other good vegetable has the same amount of Fa in it. Okay, that was just what I learned once in the past when typos occur. The next question. So the question is to Hitachi. It is typical to drive bipolar devices like IGBTs with the gate emitter voltage of plus minus 15 volt. I have instantly to make a point here. Driving an IGBT is not driving a bipolar input. That's what the IGBT is. It has a MOS input side, and so it's not like a bipolar with a current magnification. So recently, some manufacturers offer the chance to optimize their SiC module performance by using an elevated gate source voltage. Does this compromise product lifetime? Okay.
Okay, thanks very much for the question. I'm Chris White.
Chris.
I'm engineering manager for Power Device Division for Hitachi Europe. Thanks for the question. I mean, the short answer really is no, it doesn't. This is really about optimizing losses, both conduction losses and switching losses. So, for example, by elevating the on-state voltage, the gate source voltage during conduction, gives us good benefits in lowering the turn-on loss, but also lowering the conduction loss. And certainly for our devices, we've now qualified these to, for example, plus 17 volts on the gate, giving good improvement in performance, and validated that there's no impact on the reliability or the lifetime for these products. And you'll see a wide range, I think, of different voltage specifications for the gate source voltage on the market amongst different manufacturers.
Thank you, Chris. Fully agree. It's a long time when IGBTs got in place, and you might know that I was running around in the mid-80s introducing the COMFET, the first IGBT invented by Frank Wheatley and Mr. Becke from RCA. Frank and I became good friends, and so I always took a deep look into the IGBT technology. And when I look back to the COMFET, it's still a 500 volt device with 1.5 volt saturation. Was already a good device in the mid 80s. Okay, Chris, we're ready for the next. It's to EPC. We understood that GaN devices require a particular attention on the layout rules. Is this valid also for motor control designs?
Okay, Bodo, I can take this.
Okay.
It is related also to the article that I wrote for the October issue in the Bodo power system. It is true that one could think about GaN devices switching very fast, and that means layout rules need to be strictly followed. But as also Federico pointed out, when we go into motor drives, the switching speed, so the DVDT cannot be 100 volt per nanosecond. So all what we proved was that by keeping the DVDT in the range of 5 to 10 volt per nanosecond, which is the typical DVDT that is today available in motors, even in MOSFET inverter motors, then everything is becoming relaxed, and that means we can relax a little bit some layout rules that we had in the past for the CDC converter. For instance, as EPC, we always been preaching that you have to have high frequency decoupling capacitor on the same side of the GaN FET in the PCB, and simply we don't use it for motor drive. There's no need of having a high frequency decoupling capacitor on the same side. We sometimes keep some middle frequency capacitor, ceramic capacitor on the bottom side of the PCB, on the other side versus the switching cell. But again, this needs to be checked case by case, because if you do the proper layer stack up in the PCB, it could be that you don't need those capacitor at all because you don't have any ringing and your square waves are very, very good. And another common myth, especially when you're switching very fast in a DC-DC converter, is that you have to have very well balanced gate driving signal if you have a parallel of devices. And this is going to be relaxed also in motor drive. We've just launched a motor drive reference design with 4 devices in parallel per each switch. And these devices are just put in a row in the same way every hardware engineer will do and have been always doing with previous technology switches. So the answer to this question is that there are some layout rules, obviously, that you have to follow, common sense rules, but not as strict as for 1 megahertz DC-DC converter.
Thank you, Marco. Here we go. The question is addressed to all. Why all vehicle inverter run at 10 to 15 kilohertz, even wide bandgap can switch much higher? I think we heard already a couple of answers. It's a limitation for me what the motor can take to keep the system reliable.
Oh, yeah, there is a couple of things. Maybe the thing is that this kind of study takes a long time. We did on the paper that we published, we switched at 50 kilohertz, but we don't know what's the impact on the lifetime of the motor if we are switching faster for a long period of time. Maybe the impact is not so great. Maybe it is. I think there is studies with the reliability, not only on the bearings, but also the windings that needs to be taken care. That's why I was also talking about this should not be all an effort just for power electronics engineers, but also for motor designers. How can we improve in order to make the motor reliable even in these conditions? And I think that efficiency-wise, raising the switching frequency, we could have a great benefit on it, but we still have a lot of unknowns that need to be studied there.
Thank you.
May I ask a question here, or shall I throw the question in the chat group? Hello?
You can write in the chat group, and then the moderator will present the question to everybody. I understood that was the way.
Okay.
And just to complete the thing is that I think the other thing that from my side in the paper I didn't touch at all, and something that needs to be also investigated is EMI issues, because switching faster like this, probably EMI issues are going to appear. They need to be addressed. It's not that there is no solution, it's just that this is an issue at higher switching frequency.
Absolutely. And
maybe also one additional question to Guilherme, I think from Infineon side, do you see that you have already projects, real projects for motor drives where customers going this direction, wideband games with high switching frequency? Because what we see at the moment, we got a lot of requested demands, but everything, all these projects are on a research and development phase. So
yes,
customers are still trying to get experience with these wideband games. They are trying, they are asking for some samples, but so far we do not see in the short term any serious product coming for motor. Maybe for some niche applications, yes, but for these main runners, not
exactly.
so.
It's the same thing that I see. And that's why I think it's important to keep publishing on this topic and like break the bridge between these two worlds, right? Because it's not just a matter for power electronics engineers. And I think there is this barrier between us and the motor drives. And we need to prove that this can be something useful and that there is a future there, right? So yeah, I have the same vision as you. Right now is just on research. There is maybe some products that we can see that are in a more developed phase, but still like not a mainstream thing that we see on the market.
Yeah, absolutely. I think the motor drive, this motion control market, is a very conservative market. So project life cycle of the project is years. So, and here the guys, the designers are, a little bit reluctant to go for new technology. So here we have to support them and convince them and show evidences that there are also solutions for specific for this lifetime concern.
Absolutely, gentlemen. Let me look back in my younger days when I went around at motor control companies bringing the IGBT in place to be used in the inverter stage. It took a while before they really started to use IGBTs in the 80s and 90s. They still hesitated because it's a question to support their drives on a worldwide maintenance base, and if they run into a trouble, it's something they don't want. Exactly the other thing happened. I had a customer in textile machines. He used, instead of MOSFETs, IGBTs, and the result was the losses were so low that he could hermetically close the cabinet for the IGBT drive unit. And that was a textile machine with the spinning parts, and the machines are all over the globe where textile runs in spinning places. And after a couple of years, they told me that they had, by using IGBTs, brought their failures to nearly zero because there was no dust anymore in the inverters that causes the trouble mainly. So sometimes you have to put time and patience in and be constant working on it to bring it to the success. Okay, gentlemen, another story when IGBTs learned to walk on their 3 pins, not legs. The question is addressed to Infineon. What are the challenges of using wide bandgap devices on motor drive applications?
Yeah, I think we already touched some of the problems and the challenges that we have here. I would just cite the 3 that for me are the most important. So first is the bearing lifetime. We know that's going to be compromised by the switching frequency and also by the DVDT that we are using. That's one of the reasons why Marco was talking about the limitation of 5 or 10 volts per nanosecond. There is winding isolation when you are talking about switching faster and higher switching frequency. We know that the winding isolation is not done for this kind of switching frequency. So this is another aspect that needs to be addressed. And also, when you are talking about motor drives, we can be talking about different range of applications. And if we are talking about, let's say, industrial applications, then there is the cable length, because we have reflection on the cables if they are too big or too long. And these were addressed before when we were switching at 5 and 8, so 5 and 8 kilohertz. There is solutions there to avoid this. But now that we are switching faster, this is another problem that's going to come again, and we need to find solutions for it. One of the solutions is just to put the inverter as close as possible to the motor, but this is not always possible. So this is another thing that needs to be addressed there.
Let me one comment in that sense, especially when there are long cables to motor in industrial arena. What we're seeing as also is it started in the academic world, but now it's entering also in the industrial world. Is if you have a 2-level inverter, high voltage 2-level inverter, then you have 30 meters of cable going to the motor, then you have reflection. But if you start going multi-level, then the multi-level is doing a different approach to the cables, and then your reflection are limited. And this is something which is also happening in those type of application where you have long cables to the motor, and still you have high voltage inverter, but the high voltage inverter is made with low voltage devices in a multi-level fashion.
Yeah, there is a lot of different topologies that can also be. One is multi-level for sure. We can talk about current source inverter, which is something that's coming again also, where we could avoid the ripple completely on the motor. But then becomes also a problem of complexity of control, how many gate drivers you are going to use there. So there is ways to address it. The question is always the same that we were talking before, is how do you break this wall between and convince people that we have new possibilities, because people are used to do something in a way, and we need to prove that there is better ways to do it.
You mentioned the problems with the bearings.
Yes, bearings is one of the problems, yeah, because when you have partial discharging in the bearings, and if you're switching faster, you're going to have more partial discharges, and the bearing lifetime is going to be compromised.
If you use air pressure bearings, that means you have no standard normal bearings. Did you look into this? It's for special machines who have to run very smooth and accurate.
Yeah, you have ceramic coating ball bearings, for example, that avoid this problem. It's normally used for really big machines. If I'm not mistaken, I think that the motor in the Teslas also have coated ceramic bearings, but it's still too expensive. So that's the thing. For normal use applications, there is the barrier of price.
Okay. The next question will occur. Question to all. Why my wide bandgap inverter system can run with equivalent RL load, no issue, but burned on motor operation?
I have a potential answer, but you know, it's just generic. We shall see the real condition. But if you have just an RL load, you really have the resistor and the inductance. If you having a motor, there's also interwinding capacitance. And when you're switching, every time you're switching, you may have overimpose current on top of your phase current that you don't see in your RL load, but you have in the motor operation. And that is the real current you have to consider for the switching dissipation. So the phase current is for the conductive dissipation, and the switching dissipation is based on your peak capacitive current. But that could be one of the reasons. There may be different reasons. I don't know if the other gentleman here on the call can.
I mean, first thing that I thought it was controller problems. Maybe there is an overcurrent that's happening because the controller, if you're switching faster or something like a different configuration of the controller that you were using before, and you need to adapt to this new switching frequency, or it can be many things. But the first thing that I thought was controller problems.
It's also addressed to all of you. What specific design care needed when design gate driver for wide bandgap when it runs at megahertz level?
I can start this because I had some discussion and with some customer, they wanted to use silicon carbide. So we don't do silicon carbide at EPC. However, they wanted to use the silicon carbides and use quite high frequency and modulate the gate. And so they wanted to have our gallium nitride FET modulating the gate of the silicon carbide MOSFET. And to make the story short, those GaN FET needed to be switched on and off at the megahertz. And the first thing you learn when you're going above megahertz is don't use half-bridge integrated circuits, because the capacity, I mean the one which are junction isolated, because the capacitance, which is because of the inverse biasing of the junction isolation in the high voltage IC, is such big capacitance. Actually, it's small, but when it comes to megahertz or units of megahertz, tens of megahertz, it becomes predominant, it can really jeopardize completely every design, because then the gate driver will really become the hottest device, if not really burning. So first thing is, there are some technologies of gate driver that cannot be used. And so you have to decouple the level shifting function and the isolation function from the gate driver function itself. And so usually having a kind of very strong boost driver, which is just low side that you apply to the low side and to the high side, and then using a very low capacitance method to elevate the signal and isolate them.
Maybe just for my curiosity, if you talk about megahertz switching, what kind of applications can we imagine? I think mainly we're talking here about gallium nitride, I assume, rather than silicon carbide. So what can I work? What kind of applications?
There are some examples. Some example is if you want to do wireless power transfer, and there are several type of standards. Some of them are running a 6.something, a 6.7, I believe, megahertz. Some of them are 13.12 megahertz. And in the specific case I was mentioning, it was I think it was 100 kilohertz silicon carbide system inverter, where the customer wanted to really shape the voltage, the gate current at the gate of the silicon carbide. So in that case, the GaN FET that was used to do gate driving of the silicon carbide was running at 1 megahertz. And when it comes to the DC-DC converter, the DC-DC converters, which DC-DC converter are in the 1 megahertz range, and automotive DC-DC converter, for instance, for the in-cabin, they need to be above 2 megahertz, otherwise they disturbing the AM band of the radio, even if nobody's using AM band anymore. So these are some of the examples.
Thank you.
We go for the next. This question is addressed to Vincotech and Evangelos. The tested SiC power modules had single SiC devices inside or multiple parallel connected. If yes, is there any impact on the lifetime if you compare single versus multiple parallel connected SiC devices?
Yes, for this investigation that we did for the article, indeed we used a single device in the power modules. Basically, our approach is always to use multiple silicon carbide devices parallel connected rather than single devices, because in this case you achieve a much better thermal spreading at performance. And also from cost point of view, we saw that this approach is better than a single silicon device using a big chip instead of smaller chip connected in parallel. But using parallel devices, you have also to consider also a very symmetric layout to address also issues regarding high strain darkness. Coming now to the question regarding the impact on the reliability, we do not expect any, because as I said, the most important item which has to be considered in case of paralleling silicon carbide or wide bandgap MOSFETs is the symmetry. So very good symmetric layout can achieve low strain darkness, but very homogeneous how to say temperature of the devices, because for the power cycle capability, the weakest link in the chain is the chip with the highest T-junction max. So if you have parallel devices, then you have a very bad layout, then it could be that one of these parallel chips showing the highest junction temperature, and this one will be the first that will fail during a power cycle test. So you have to achieve even current distribution among the chips, which will result in a similar T-junction maximum temperature for all of the chip. Then as a result, then there is no reliability issue in terms of power cycle capability compared with single with a parallel device.
Thank you, Evangelos. A question to all again: is there any successful case to integrate gate driver into the wide bandgap power switch on one chip?
So may I start on this?
Yes.
So when you talk about gallium nitride technology, there's in the lateral gallium nitride technology is helping in doing integration and integrating power elements together with, let's say, gate driving control elements. So at EPC, we started doing first just the integration of two power devices in the same die, so high side and low side device already in 2014. Then in 2019, we introduced the first e-power stage, which is half bridge gate driver junction isolated with the low side and the high side power devices in one single die. And that is complete gallium nitride technology. So it's integrated circuit technology on gallium nitride, not on silicon. And so the answer is yes, this is already there. In 2022, we released the new family, which is 100 volt, and it's also again based on purely gallium nitride integrated circuits. But we are not alone on this. There are also solutions like co-packaging in the same package. The gate driver made with a silicon technology and then using gallium nitride devices.
Thank you, Marco. To all of you, what's the method to have sensorless estimation for junction temperature for wide bandgap?
I'm not sure if I got this question. Is it during the operation or is it during in the laboratory? Because for laboratory there are some solutions, but during the real life,
all the real life application comes from lab and theoretic. That's my comment. Thank you.
If I can just comment is that usually in a MOSFET, one thing that is done is having even online, having a quick measurement of the body diode drop, which is giving an idea of the temperature as long as somebody made upfront a characterization of the same MOSFET. But in any case, and I'm talking about gallium nitride FET. I don't know about silicon carbide MOSFET, then the gentleman here can comment on this. In gallium nitride is slightly more difficult if you want to do it that way. So there are other techniques, and at EPC we are working on those techniques, but I cannot go more in detail because we are basically making a disclosure for patenting.
Thank you, Marco.
If the RDS-on estimation method is mature, is that possible? How do you think about using RDS-on to estimate the junction temperature?
Yeah, that's repeatable also, but I believe that with GaN FET in the future, we will be able to do more accurate things than just do, because if you want to estimate the RDS-on, it means you have to do interact somewhat way with the device to measure the drop when it's working. There are other ways, but yes, that's possible. That's possible to be done.
Thank you. Very good. Thank you.
The next question comes up. What is the challenges currently that bring the wide bandgap product yield low or cost high?
I guess I can start on that for SiC, looking at high power SiC, and the big thing driving the cost of that is the raw material inputs. You know, raw wafers for SiC are inherently more expensive than silicon wafers for IGBT, and that drives a large proportion of the product cost, certainly at the high voltage level. Yield is an impact, of course, but that's improving all the time.
Let me specify. Maybe I asked the wrong verbiage. Okay, so forget about the material. Think about the process. All your steps. Which steps is the most challenging that limit your yield? Is that a better question?
I'm not sure that's something I'm able to discuss here.
Yeah, I would say that this is a really matter that we cannot discuss openly, I think.
And I also want to ask the audience to bring the questions in by email, by chat, and we will answer here as far as it is possible, but not to things which are not able to be under some disclosure agreements of production. That's okay. We get the next question. What are the challenges behind electro-vehicle traction inverter based on GaN technology, and what are the advantages over SiC inverters?
Okay, maybe I can start here talking about what challenge. So generally speaking, I think that the highest voltage GaN that we have in the market right now is 650. Generally speaking, we have normally electric vehicles that are 800 voltage battery. So either you go to a multi-level structure, or you are going to need to go to SiC or IGBTs. Second thing is that I'm not 100% sure that there is already any automotive certified GaN in the market right now. I know that people are working on it, but I'm not 100% sure that they are already certified. So I think that this is the two most important challenges right now. I think that the second one is probably on the way of being fixed, but the first one about the 800 volts battery, this is a more complicated problem because the highest voltage of GaN is 650 right now.
I just got from my backstage that we have the last question coming up. So, question to all. What's the next generation after SiC and GaN? What's in your mind?
To be honest, yeah, on my side, I think we still need to fully understand what are the capabilities of SiC and GaN. I think we are not nearly there. I mean, for silicon, how many years we had until we get to the point that we are now. So until we get to the full capabilities of SiC and GaN is going to take at least, I would say, 10 to 20 years.
I
fully agree.
I can add one thing. In reality, now we have these new technologies, okay? So it took, I will say, 30 to 40 years for the power electronics to evolve in the way it evolved, thanks to silicon technology on the power and thanks also on the control side, because in 2000, there were not the computational power that we have today. And what I see, for instance, motor drives world is completely digital since 2000, while I will say the converter world, DC-DC converter world is becoming digital nowadays. Many controllers are still analog. I still believe that everything that was generated so far was based on, let's say, intrinsic limitation of the silicon MOSFET technology. And with these new technologies, I would assume that topologies and even, for instance, motors could radically change. I always ask motor manufacturers, why are you doing a three-phase motor with the 500 amps each phase? Can you do multi-phase and doing different? And the answer is simply, we always been doing like this. And I think that is what is going to change, I hope, in the future, so that all these technologies and topologies going to change, take advantage of the new technologies. As Guilherme was saying before, that was about the, for instance, current source inverter. Current source inverter always been on the books, but there was no bidirectional blocking device available in the technology. When you start working with gallium nitride, you can have theoretically, and now parts are also coming out, bidirectional blocking voltage and bidirectional current devices that may open the road to current source inverters. So these things may happen even before we talk about the next technology on a solid state or whatever it is.
Yeah, I think first we need to fully explore this and
exactly
see the impact on the applications and also what's going to happen to the market before thinking about what's the next generation of semiconductors.
Fully agree. And last comment from my side, I think the approach that we are following here at Vincotech is for sure we are investigating this new technology, silicon carbide, gallium nitride. But still, if a customer comes to us and asks, "Can I have silicon carbide module or gallium nitride?" We're asking why. What is the application? What is the issue that you would like to solve? And we try still to push here the technology for silicon to the end, because we still believe that also already with silicon we can solve some issues, and it's not need to switch to this one. So
Absolutely.
Before to think about new generations, let's utilize or push to the physical to the end the existing technology, convince customer. Now we have the silicon carbide, we have gallium nitride, so we are two very nice technologies, and yeah, let's see what will be the next.
None of us has a glass ball magic to look into and see what the future will be. That's very little incremental steps to look for when they occur. My backstage gave me the sign that the session had come to an end. Gentlemen, I say thank you, and I'm looking forward to see you at my wide bandgap conference in Rio in the Hilton in December at the Munich airport. Have a nice rest of the week and enjoy the rest of the day. Goodbye for now.
Thank you
Thanks
very
a
much.
lot. Welcome.
Thanks very much.
Bye-bye.
Bye.
Thank you, everybody.
Bye.
Thank you.
Bye.
Bye-bye.